Okay, good afternoon, guys. Okay. So first, I wanted to ask you guys if you had a chance to look at assignment 4. Well, even if you haven't, I guess it's okay. Okay, no problem. Let's at least try and spend like a few minutes to get to at least have a plan. Okay. And then, well, it's still up to you to work on it, but at least you have I will try and give you some ideas. So question 1, this is assignment 4, 3274. And then question 1 says, prove for all MKN that if M is less than N, then M plus K is less than N plus K. Okay, this is just one example of, many properties which involve less than and addition and multiplication and stuff like that. Okay. Okay. So in the question I said prove by induction. I guess the question is, there's like 3 different variables. So I guess we should ask induction, what should we do induction on? Oh yeah, this is all MK and N in the natural numbers. Okay, yeah. That's a good idea. What's a good, this kind of makes sense to try induction on K. Well, the best way to see that it makes sense is to try it, and then if it works, it was the right way, but it kind of makes sense because if K equals 0, that's base case, and the base case is also not too hard, so we do induction on K. That means P of K is the statement, if M is less than N, then M plus K is less than N plus K. And then we'll prove this for all M and N. And then you prove it for K equals 0. You assume it's true for K, and then you prove it for K plus 1. Okay, so you have the base case. If M is less than N, then M plus 0 is less than N plus 0. And how do you prove that? Well, M plus 0 is just M. N plus 0 is just N. So this is kind of already true. You just say, So you just say m plus 0 equals m, n plus 0 equals n by definition of addition, then you're done. Okay, so that's the base case. Then you assume if m is less than n, then m plus k is less than n plus k. And then the main part, the hard part is, well, I wouldn't say it's that hard, but we'll try it. The induction, this is the induction hypothesis, and then the induction step. You suppose m is less than n, and then you try to prove m plus k plus 1 is less than n plus k plus 1. Okay. And there are, different ways to go about this. So I would like you to try them, see what works. Okay. So does anyone have any, so of course there's like work that goes there. Okay, so I guess I want to say something also about question 2. Question 2. What is the statement of question 2? You have to prove for all natural numbers m and n, if m is less than n, then there exists k with n is equal to m plus k. Okay, and essentially, this is what allowed, like, from this, we could define, like, subtraction. Once we solve this question, we could then define, we'd have the power to define k. We would say, like, n minus m is the number k. Right? If we don't know k exists, then we don't know what n minus m is. Like, before you can define 5 minus 3, you have to know that there's this number 2, and 3 plus 2 equals 5. If you don't know that 3 plus 2 equals 5, you can't talk about, what did I say? 5 minus 3. Okay. Right. And from this question, you can also prove the cancellation law. Like, if m plus k equals n plus k, then n equals m, stuff like that. Okay, so the solution. Well, probably we should do this by induction. It's pretty safe to start there. We could try induction on n. Okay. I'm not sure if that's the best way, but we could try it. So P of n would be the statement that if m is less than n, then there exists k such that m plus k equals n. And the base case, n equals 0, is trivial because there's nothing less than 0. Okay, and then you assume if m is less than n, then there exists k such that n equals m plus k, and now you try and prove the same thing, but for n plus 1 instead of n. Okay, so now you have induction step. Suppose m is less than n plus 1. And now we know from class that if m is less than n plus 1, it's either less than n or it's equal to n. Well, the case m equals n is clear. We should just take k equals 1. Take k equals 1, then m plus 1 is n plus 1. So we've solved the equation n plus k equals n plus 1. Okay. Okay, so the case of m less than n, well, from that, you know, the induction hypothesis would tell you that n equals m plus k, and now n plus 1 equals m plus what? Well, I'll let you fill in that. And also, I'll let you also make everything look nice. Okay? But so once we prove this, then we can talk about stuff like you know, n minus 2 and all these things. But just starting from the natural numbers, you know, it's like it's kind of like you know, breaking the rules or something to talk about subtraction before this point. Like, you know, we had to do all this work for addition, and in the same sense, you don't get subtraction for free. You have to, you know, we have to build it. Okay. So did anyone have any questions about those two questions on the assignment, or the other questions too? Okay. Okay, so do you have to word it like me? No, you don't. You have to word it somehow though. Yeah, like you do have to use words. You don't have to use my words. Yeah, but that is a good question. Okay. Oh yeah, so just in case you didn't see, the question was, do we have to word it like me? And the answer is no. You don't have to. Okay. Actually, because so here, let's just take a break. I know we'll just take a very short break. Because after this, I just want to move on with, you know, I wanted to prove the least upper bound property for the real numbers. And so I think it's good to just leave this in its own section, and then when we start back after the very short break, it'll be talking about the least upper bound property. Okay, so this is just so that I don't run over the 40-minute limit for Zoom. Okay, so we will start back in like, well, I'll start back teaching in talking really, but I'll start back in 3 minutes. Okay, so try and take a little break. Okay, bye.